Mystica. A radio telescope once printed a signal so strange an astronomer wrote, "Wow," right on the paper. It lasted just over a minute. It was recorded in the data, and then it never came back. So here's the documented gap. If you only catch it once, how do you prove where it came from? Tonight we'll follow logs, timelines, and what researchers can actually verify. And we'll keep speculation on a short leash. Now, one ground rule before we start. Radio astronomy is a constant fight against interference. And the cleanest signals are often the ones that fool people first. Airports, satellites, electronics, and even distant transmitters can slip into telescope data in ways that look convincing. So when a clean, narrow tone appears, the first question is usually not who sent it, but could we have made it? That brings us to an older lesson that still matters. In the late 1960s, astronomers noticed pulses so regular that they briefly joked about an intelligent source. Those pulses were documented, they repeated, and their timing looked almost too perfect. Here's the problem. Perfect timing is not proof of intention. Follow-up evidence showed the source was natural, tied to rapidly spinning neutron stars, later called pulsars. So the field learned something uncomfortable early on. Nature can sound engineered. Now, keep that in mind, because it frames the most famous one-time signal in radio history. In the late 1970s, a survey telescope recorded a strong, narrow-band spike that stood out from everything around it. The printout showed it rising and falling in a way consistent with a sky source drifting through the telescope's field of view. But the record also shows the brutal part. There was no immediate second look at the same place at the same moment. Without a repeat, you can't triangulate. Without a repeat, you're left with a time, a frequency, and a region of sky. And a long list of possibilities. Now, this is where most untraceable cases are born. A single detection can be genuine and still be untraceable, simply because the universe doesn't schedule reruns. So the next question is obvious. What about signals that repeat, where you should be able to chase them down? That brings us to a different category. One that exists outside telescopes and inside the ordinary radio world. For decades, listeners have documented shortwave stations that transmit patterns with no confirmed public explanation. Some are called number stations because recordings include spoken strings of numbers or coded phrases. They're logged, archived, and discussed for years, but operators are rarely confirmed in public records. One well-known example is a persistent buzzing signal on a fixed shortwave frequency, often nicknamed the buzzer. It has a long history of reception reports and recordings across the monitoring community. Here's the gap. It repeats. But public certainty about the source and purpose is still limited. Now, why can a repeating signal still feel untraceable? Radio waves bounce, reflect, and travel oddly depending on conditions, time of day, and the atmosphere. Direction finding can be difficult when signals propagate by skipping and reflecting over long distances. And strong terrestrial signals can appear to come from places they are not actually originating from. So, repeatable does not always mean easy to pin down. That brings us back to the scientific side, where the mysteries arrive fast and vanish faster. In the mid-2000s, researchers reported extremely short, extremely bright radio pulses found in telescope data. Some were over in milliseconds, but their signatures suggested they had traveled through a lot of material on the way to Earth. Scientists began calling these events fast radio bursts, sometimes shortened to FRB. At first, the frustration was simple. Telescopes were detecting bursts, but not pinpointing a precise source. If your sky map is too wide, you can't point to one object. You can only say, something happened somewhere in this region. And that's not enough to close a case. Now, here's the problem that turns excitement into caution. A burst that happens once can look dramatic, but it can also be a false lead if you can't confirm it independently. So researchers pushed for repeat detections, better localization, and cross-checks across instruments. Then something changed, and it changed the story. Some fast radio bursts were found to repeat. Repeaters mattered because teams could schedule follow-ups and coordinate multiple instruments on the same target. Over time, some repeating sources were localized to host galaxies. So yes, parts of the mystery got pinned down, but another part stayed open, because knowing the address is not always the same as knowing the engine. Now, what might produce such bursts? Researchers have proposed leading explanations in the scientific literature, including highly magnetized neutron stars called magnetars. In 2020, teams reported a bright radio burst from a magnetar in our own galaxy that resembled fast radio bursts in important ways. That strengthened the idea that magnetars can produce at least some fast radio burst-like signals. But the record still doesn't reduce every burst to one simple story, because different sources behave differently. That brings us to an important reminder about how science protects itself. For a while, some observatories recorded bursts that looked like fast radio bursts, but only at one site. They were logged, they were analyzed, and they caused real confusion. Later, investigators traced many of those events to a local source linked to microwave ovens opened at the wrong moment. Those false signals became known as peritons, and they were a painful but valuable lesson. Here's why it matters. A signal can look cosmic and still be local. So the next question is, how do researchers separate unknown from untraceable? In research language, unknown often means there is not enough data to decide, and untraceable often means you can't localize it well enough, or you can't repeat it reliably, or you can't rule out interference. Now, let's talk about the signals people most want to be intentional. Search programs look for narrowband tones, patterns, and frequency drift consistent with a moving source. But the record shows an irony. Human interference can produce the cleanest looking lines. Satellites, transmitters, and everyday electronics can imitate the exact shapes researchers are trained to notice. That brings us to modern candidate detections that make headlines and then change status after deeper analysis. In recent years, researchers have flagged unusual narrowband candidates in telescope data and announced follow-up work. In some cases, later analysis pointed toward terrestrial interference as the more likely explanation. So the story becomes cautionary, not conspiratorial. A claim that survives is rare, because the filter is harsh by design. Now, we're going to tighten this into a simple map you can remember. What actually makes a signal traceable? First, you want repeat detections, ideally from different observatories. Second, you want a tight position on the sky, not just a broad region. Third, you want instrument logs that can be audited, including timestamps, pointing coordinates, and receiver settings. And fourth, you want a clear path to rule out the boring stuff: local electronics, satellites, aircraft, reflections, and propagation tricks. If you don't have those pieces, you're stuck with a documented event and a documented limit. Now, go back to that famous WOW printout with that in mind. It's compelling not just because it's strange, but because it is a perfect example of a data-shaped mystery. There's enough to be real. There's not enough to be finished. And that tension between what was recorded and what can be proven is what keeps the file alive. Now, here's one more angle that matters for retention, because it's the part most people never hear. When someone says, scientists still can't trace it, it can sound like a locked door, but often it's simply an incomplete map. A one-time detection is like hearing one clear sentence through a wall. You can't identify the speaker from that alone. A repeating transmission with no confirmed public attribution is like a phone ringing from a blocked number. It's real, but it's not signed. A cosmic burst localized to a galaxy is like a flash far away. You can point to the neighborhood, not the switch that caused it. Now, bring that back to the opening question. Who could be transmitting? The most honest answer is, the record often doesn't justify naming one suspect. Sometimes it's a rare natural event that doesn't repeat on our schedule. Sometimes it's human interference wearing a perfect disguise. Sometimes it's a known category with an unknown mechanism. And sometimes it's simply not enough information to close the loop. That brings us to the simplest test you can use on any headline. When you hear untraceable signal, ask what's missing. Is it a second detection that confirms it was not a one-off? Is it a tighter sky position that points to one object instead of a region? Is it independent confirmation from another instrument in another place? Is it a clean way to rule out interference with full logs and hardware checks? Because the mystery isn't just the signal, it's the gap between data and proof. Now, remember the first image, the printout, the handwritten "wow," and the silence after. That case still holds because it shows how a real record can end without resolution. And it also shows why researchers stay careful. Because the universe is loud, and our world is louder. So when the next unidentified signal appears, the outcome will depend on speed and coordination. If multiple telescopes catch it at once, localization can happen fast. If it repeats on a pattern, follow-ups can tighten the target and shrink the uncertainty. If it never returns, it may join the one-time files and stay open for decades. And until that gap closes, the most responsible ending sounds almost boring. Documented, analyzed, and still unresolved. Or, if you want more cases where the logs are real but the answers don't land, subscribe for real, unexplained mysteries. Next time, we'll follow another file where the timeline is clean, the evidence is solid, and the conclusion is still missing.